Okay, welcome to Note Set 12, where we'll expand our understanding of the ideas we've been growing here a little bit further. We'll be looking at something called the LU decomposition or LU factorization. Basically, we're looking at breaking our matrix A into the product of two matrices, L and U, where L is lower triangular and U is upper triangular. So breaking a matrix into parts is a very important step in a lot of algorithms, primarily because it leads to some nice computationally efficient approaches to solve things. But all throughout control systems, signal processing, communication systems, networking, all sorts of things that electrical and computer engineers do. And I'm drawing views here from areas I'm familiar with, and there are other areas of EE and COE that I'm not as familiar with. So I'm sure that this is in those areas as well. Decomposing a matrix into some parts is kind of key to understanding the structure of a problem and figuring out better ways to do things, more efficient ways to do things. So again, I'm stressing here that our job as engineers is not just to learn how to compute a number or even a matrix full of numbers. It's to understand how this all works, because understanding how things work enables us to be innovative engineers. So this material is in section 2.6 of your textbook. So let's just kind of muse generally here about factorization. And you may be familiar with factorization of integers. So we could say, well, we're going to find the factors of 4. So we can factor it into 2 times 2. In fact, factorization of prime numbers shows up in cryptography. So if you're familiar with that, you'll know that the idea of factorization is kind of key to a very important problem in computer science and computer engineering. A lot of times in engineering, we need to factor polynomials. So when you look at control systems, signal processing, communications, computer networks, things like that, the key to understanding how those systems work and how they'll behave might boil down to factoring some polynomial. So just showing an example here, we have this polynomial in A and B. We can factor it into A plus B and A minus B. So once we factor this, we can see something more interesting here about that. Suppose this was really x squared minus b squared. Now we can say x plus b and x minus b. And if we treat x as our variable, we can now see that the root of this polynomial, there's 2 roots, one at plus b and one at negative b. So factoring polynomials is kind of key. If you've already studied differential equations, you know that understanding the behavior of a certain type of linear constant coefficient differential equation boiled down to finding the characteristic polynomial and then finding the roots of that. So finding the roots is facilitated by factorization. And also later in this course, when we talk about something called eigenvalues, which is a huge useful tool in engineering, crops up all the time, we'll discover that there's a polynomial involved there. And in fact, it's actually closely related to the polynomial that's the characteristic polynomial that you find in differential equations. So lurking inside all of this stuff is a lot of connections to things that as you go through your higher level courses, you should be going, oh, I remember that from back there. That's connected to this? So cool. But we're talking about factorization of matrices. So we sometimes call this a decomposition. But basically what we're trying to do is same kind of thing. Factor a matrix into a product of two different individual matrices, or maybe even more than two. So there's many different factorizations available, but the one that we're going to talk about is the LU decomposition. And, I say here that it's the most important in practice. Yeah, it's one of the most important. There's a few others. The eigenvalue decomposition, the singular value decomposition. Those are real workhorses as well. So basically in the LU decomposition, what we're looking for are two matrices, L and U. Both are triangular matrices, and, well, L is a lower triangle. That's why we use the L. And, yep, you guessed it, U is an upper triangular matrix. And so what we're trying to do is decompose A into the product of a lower triangular times an upper triangular. And this should be no surprise that it's connected to the process of elimination, since when we did elimination, we were aiming to end up with an upper triangular matrix. So you can kind of see that, we're building here. We started with a simple concept elimination, which you were probably familiar with from a less formal view of it. Then we built that into, we can do elimination with matrices. We can use elimination ideas to compute the inverse of a matrix. And now we'll see that we can use these ideas to end up with a decomposition of a matrix. So A is equal to LU. Our job is to find the L and to find the U given a particular A. So the U is going to come from things that we've already seen. It'll be the upper triangular matrix that we've been getting from elimination. And if you remember, we saw that ends up having the pivots on its diagonal. And then the L, believe it or not, will be a lower triangular matrix that has all those multipliers that we use to create the upper triangular matrix. So all the multipliers that we use will fill the lower entries of the L matrix. So these are the multipliers that we use to multiply the current pivot row and then subtract from the row that we're trying to cancel something in. So that's the key idea. So really we already know how to find both of these. We just need to recognize that what we are doing is actually this. So there's our A is equal to LU. And let's do a numerical example. Always start with a simple one. So here's a 2 by 2. And we'll talk about two different directions. So first we'll go forward from A to U. This is just our standard elimination. So we want to eliminate the 6, turn it into a 0. So our pivot is 2. So we take 6 divided by 2 gives us 3. So we're going to subtract 3 times row 1. So remember, 3 is our multiplier. 3 times row 1 gets subtracted from row 2 and gets replaced in row 2. So when we do that, what is our elimination matrix? Well, it's going to look like that. So remember, the negative sign here comes from the subtraction part of this. So that's what we're saying here. Pay attention. This is the negative of the multiplier. So the multiplier is really 3. So it'll be this number, the positive 3, that will show up in our L matrix. So here's our numerical example. Let's go backward from U to A and see how that works. So if we had let me back up here. As we have here, we have E21 times A gives us U. Well, to get A back, what we need to do is multiply from the left by the inverse of E21, and that means we would also put that in there as well. So A would be the E21 inverse times U, and that's what we're showing here. So E21 inverse times U. So here's our U that we just found. That was the upper triangular result from doing elimination. And you can verify that this is indeed the inverse of that. But notice all I did was I took the -3 and turned it into a +3. And so all I'm really doing is this. I started with E times A is equal to U. I'm doing the inverse of E. I get A on this side, and I get E inverse U on that side. And we can think about why we need a positive L21 there, because that's going to undo the negative multiplier. So you can kind of verify that by actually doing the matrix multiplication. So if we do this out, we can see that yes, indeed, we do actually get the A. And look what we have. We've got a lower triangular matrix times an upper triangular matrix. So that's our factorization. We've got L times U is equal to A. So we've seen this with a 2x2 matrix. For larger matrices, there will be a whole string of E matrices that will string together to get to turn A into the U, and then the L matrix will be composed of a sequence of all the inverses of the E matrices that were used. And it's easy to write down what the E sub j's will be. So each matrix will generate a 0 in the ij position. And for a 3x3 matrix, assuming that there are no already zeroed elements, we'll need 3 E's. And so, this sequence 2, 1, 3, 1. So that's, we know that it has to be 2, 1, 3, 1, right? Because this is using the first row to cancel out the first position of the second row. Then this is using the first row to cancel out the first position of the third row. Then we're going to use the second row of that resulting matrix to cancel out the second position of the third row, and so on. And so if we want to solve this for A, we need to essentially swing these, quote unquote, swing these over to the other side. Well, that involves applying these inverses. Just like we would expect. And just as we should expect, these go in the opposite order. So here we applied 2, 1 first, all the way out to 3, 2 last. Well, here we apply 3, 2 first, the inverse of 3, 2 first, and then the inverse of 2, 1 last. So remember, we put on socks, put on shoes, take off socks. And that gives us the A is equal to LU. And, here we assume that there were no row exchanges involved, but, it is possible to do this if there are row exchanges involved as well. So let's just look at this a little bit deeper. So here's that same scenario, and we can find some interesting properties here. So observation number 1, when we looked at these, the inverse matrix, every E inverse is itself a lower triangular matrix. So the E's are triangular, lower triangular, and the E inverses are triangular. Its off diagonal entry is Lij, and that just undoes the subtraction produced by that. And also the main diagonals of these things all contain one of both E and the E inverses. So it's very easy to figure out what these things look like. And it's also easy to show that a lower triangular product of inverses is L. So, if we take all these E inverses and multiply them, we can show that we always get something that's lower triangular. Then observation number 3, each multiplier Lij just goes right into the Ij position. So usually when we do matrix multiplication and matrix inversion, usually when we do matrix inversion, things get all mixed up, and then when we multiply a bunch of matrices together, the numbers all get mixed up. But because of the special structure here, they don't get mixed up. They just end up going right in where they're supposed to go. So here's an example. We can immediately, if we figure out what the different elimination matrices are, you'll find out that the multiplier to zero this out will be a negative 1/2, and so a positive 1/2 goes right in there. We didn't need anything to zero that out, so a 0 goes in there, and then the multiplier to zero this out. Remember, we're not operating on this row anymore. It has to be done on the new row after we've zeroed that element out. And if you look at that, you'll find out that the multiplier was negative 2/3 to zero this one out. And so we put in a positive 2/3 in the location of the thing that we're trying to zero out. If you go through and you figure out what your multipliers are, you'll know exactly where to put them in the matrix. And so that would be our L. That's lower triangular. So we've got this section filled in. And then we've got U, which is this section filled in. And so that's our L times U. As we saw before, the things that go down the diagonal are the pivots. So, just saying or explaining or writing out what we did here, the elimination subtracts 1/2 times row 1 from row 2. And we subtract 2/3 times the new row 2 from row 3. So that's why those things end up there. So to just summarize this, the LU decomposition is just elimination without any row exchanges. So the upper triangular U has the pivots on its diagonal. Lower L has all ones on its diagonal. And the L has the multipliers below the diagonal. So here's a 4x4 matrix. We can expand it this way. You can go through the steps. So there's our lower diagonal, and there's our upper diagonal. So a few extra observations here. So these are true for this example, but they're also general things. So when a row of A starts with zeros, so here this starts with 1 0, so does that row of L. So that row of L starts with 1 0. This starts with 2 zeros, so this row of L starts with 2 zeros. When a column of A starts with zeros, so does that column of U. So this column of A has 1 0 there, so this has 1, this has 2, and this has 2. And if we take advantage of that, if we write any computer program to do this, we can recognize that and we don't have to bother doing that. So basically we're just saying, look, we know that those are already zeroed out, so we don't have to work to zero them out. We can just immediately figure out what those have to be. So let's look at this and see if we can figure out the key reason of why A equals L times U. Well, we did kind of already explain that, but this is just another way to look at it. If we think about the pivot rows that we subtract from the lower rows, except in the first case, they're not the original row of A, because the action of previous eliminations have changed them. So what we can see is that we're really using the previous rows of U, not A. So what that really tells us is that this first row of U is really just the first row of A. But then the next row of U is changed. And here we show the equation for row 3 of U. Row 3 of U is going to be row 3 of A. So that's the row we're trying to modify, and then we've got 2 zeros that we need to zero out, the one in the first position and the one in the second position. So we use row 1 not of A, but row 1 of U and row 2 of U. So that's the elimination to get the first 0, and that second term is the elimination to get the second 0. And so if we just rewrite this to get back to row 3 of A, we see that we're basically using the L values from the L matrix operating on all 3 rows of the U matrix. So we can easily say that row 3 of A has to be equal to that. And notice that this is row 3 of the L matrix. So it's pretty clear that this thing is working the way that it should work, and kind of see why it has to work that way. Now, there's an alternate form called the LDU decomposition. So this is motivated by the fact that the LU factorization is not, I put this in quotes, symmetric, because I don't want you to think about symmetric matrices. I just want you to think about the form of L and the form of U. Even though one is lower and one is upper, there's something else that's different about them, that's kind of asymmetrical about this. If we go back and look at this, remember, see here is, if we look at this U, there are there are general numbers there on the diagonal, but the L always has values of 1 on the diagonal. And so that sets up kind of a asymmetry between their forms. But here's what we can do. If we take that U matrix that has in general non-unity values down its diagonal, we can just divide the U, each row of U, by the first element, the first non-zero element in it. That's equivalent to basically factoring out a diagonal matrix that contains the pivots. So what we can do is decompose U into, well, we're dividing by this number here, and so that makes that first element 1. Then we take U12 and divide it by D1, which remember was the element that was here. So it's the 1 element of the original U, and so on. And notice that everything on this first row gets divided by D1. Then everything on the second row gets divided by D2, all the way down to everything on the nth row gets divided by D1. Well, there's only going to be one element there, and that normalizes that. Then we pull out a diagonal matrix. So this is our diagonal matrix D right here. So everything out here is 0, everything out here is 0. The only thing we have are non-zero values down the diagonal. And so those are actually the pivots right there. So I know they're going to be non-zero. So we can factor either way. If you see it written as LU, you know that the U is going to have the pivots down the diagonal. If you see it as LDU, even though we're using the same symbol, these two U's are not the same. The two L's are the same, but the two U's are not the same. So if you see it written as LDU, you know that the U is going to have ones down its diagonal. So here's an example. We've already, on the left side, we've already factored it into these two matrices multiplied times each other. So this is the L, and this is the U. And then if we take this first row and divide it by 2, we get 1 and 4, and we'll have to have a 2 on the diagonal. And then we take this row and divide it by 5, so we get a 1 there, and we get a 5 on the diagonal. So that's our LDU decomposition. Okay, so we want to spend a little time talking about the cost of doing this, since this is an important operation that shows up in a lot of engineering algorithms for doing things, signal processing, control systems, networking, things like that, circuit analysis. We want to find out how much computational cost this is going to take. So to study that, well, we want to first talk about, what do we mean by cost? So how much computing time, how many computations we have to do. So we don't actually compute, or we don't actually calculate the time that it takes, because that'll depend upon the specific processor that you have. But we count how many operations are necessary to do this, how many fundamental computer operations. And we usually just count like additions and multiplications. And then once you know that, you can figure out roughly how long your particular computing system will take. Now there's some other things involved, like time for storage and fetching and memory access and various other overheads inside your computer. But it's pretty common, since we won't know precisely what kind of computer it's going to go on, to compare the complexity of different algorithms simply based upon the number of additions and multiplications. And by additions, we also mean obviously subtractions, and divisions would be counted as multiplications. So let's first look at doing the left side of AX is equal to B. So the first stage of elimination produces all the zeros below the first pivot. So for every one of those zeros requires one multiplication and one subtraction. And we're going to cheat and count that as n squared multiplies and n squared additions or subtractions. So there's a little picture. So to zero this out, to make this 0, we would need to multiply all of these numbers by by a number, and then and multiply or add to this row, and so on and so on and so on. So the actual number is more like n squared minus n, but it's common in these kinds of things to only worry about what does this look like when n gets really, really big. So when n goes to infinity, n squared grows much, much faster than n. So this quantity will look an awful lot like n squared as n gets really, really big. So that's a common trick to do. And then the elimination on column 2, we can, once we've eliminated all of these, we can kind of say, well, I've just got this little chunk to deal with, and I need to eliminate all of these. So it's like having an n-1 size problem. So we can think of the size of our new quote-unquote working matrix as n-1. And so using the same argument in approximations, the cost of that stage will be n-1, and so on and so on. So we'll have, in order to do the elimination to get the u part of this, we'll have n squared from the first stage, n-1 squared from the second stage, and so on, all the way down to 1 squared. And when n is, if we apply a result, well, let me back up here. You can find a result for the sum of the first n squares, and it will tell you that it has this form. So that's a nice result. There's lots of results out there in the math literature, in math books, online, whatever, that tell you, a closed form solution for these summation type things. Some of the, first n integers, the sum of the first n squares, or first n integers squared, and so on and so on and so on. And then we look at this, and here's, again, saying, we only care about roughly what's happening as n gets really, really large. So when n gets large, this might be like 1,000 plus a half. Does that really matter? And 1,000 plus 1, does that really matter? So we can kind of ignore the plus 1/2 and the plus 1. And so we see that we get n cubed. So we've got n cubed over 3, or 1/3 n cubed multiplications, and 1/3 n cubed subtractions, or sometimes we just refer to those as multiplications. So that's actually a pretty high cost. When we see things that go as the cube of the size of our matrix, we start to get worried. Even the square can get large pretty fast. Ideally, we love it when things go up as the first power of the size of a problem, but that doesn't happen very often. But cubed is when we start saying, wow, we're going to pay an awful lot to do this, but sometimes we have to do that. So what about the right side of B? That was just to do to compute the U matrix after elimination. So we do the similar kind of thing. We're going to have to subtract multiples of B1 from all the components below it. That's going to take n-1 steps, and then the second stage after that would be n-2, and then n-3, and so on. So that's going to give something that looks like that. And then the last step that we have to do is back substitution. So for the when we solve for the last variable, we just have to do one thing. Then all the way up to well, let me say it this way: for xn we only need one step. For xn-1 we need 2. All the way up to x1 we need n steps, and so that leads to something that looks like that. And so if we combine all this stuff together, we get that gives us n squared. And so to solve the right side, we need n squared multiplications and n squared subtractions. So so we can see, if we compare this, the left side is something that's like, well, we say of the order of n cubed, or on the order of n cubed, even though it's 1/3 n cubed. We're mostly interested in like the order of it. So the left side is order n cubed, the right side is order n squared. So even though that n squared is going up pretty quick, that n cube's going up even faster. So that's the thing that dominates it. So the whole thing is going to be like order n cubed, is how engineers and computer scientists would refer to that. And so once we know that this thing is order n cubed, we know that if we make a matrix 10 times larger, so we've got one matrix that's a 10 by 10, we go up to a matrix that's 100 by 100, it's going to get 1,000 times more computation. So 1,000 times longer. Now that might not seem like very much, but you know, if you had that 10 by 10 matrix and you could do it in a second, you're going to do the 100 by 100, just 10 times bigger. You're going to do 1,000 seconds. That's a fairly long time. So, you know, we went from 1 second to 1,000 seconds. So I just pulled out my phone here to do a little bit of calculation here. So 1,000 seconds divided by 60 seconds per minute. That's almost 17 minutes. So we went from 1 second to 17 minutes just by going to something 10 times longer. You know, again, that's just assuming that it would take us 1 second to do the 10 by 10. Probably not. It might only take a millisecond to do the 10 by 10. But still, you get the idea. 1 second versus 17 minutes. That sits in your head, and you understand what that means. So if you went from 1 millisecond, you'd go to 17 milliminutes, even though people don't usually talk about milliminutes. So I don't really know how long that would be, but yeah, well, it'd be you'd go from 1 millisecond to 1,000 milliseconds. So that's 1 second. So you go from a millisecond to a second. All right, so we'll stop here, and I'll see you in the next set of notes.